All right. Hey, everybody. So in this video, we are going to continue our conversation about power series, and we're going to try to explore more deeply the main idea of thinking about power series as a function. We're going to identify a handful of functions, things like polynomials, and how they can be associated with certain power series. And importantly, we're going to define how integration and differentiation works with power series. So here is sort of the angle that I'm coming at this video from. The power series, as we defined last time, is the sum, or is this expression, sum as n goes from 0 to infinity of c sub n times x minus a to the n, right? So this is a function in the sense that you can plug in a value x and you can get out a meaningful number as your output as long as the x value you're plugging in is within the radius of convergence for the given power series, right? So in other words, this expression, capital F of x, is a well-defined function. And what that means is that we should be able to talk about some of our favorite function attributes in regards to this power series. Things like, is f continuous? Can we take a derivative? Is it differentiable? Can we calculate its second derivative? Is f of x increasing, decreasing? Can we find an antiderivative? All these fun things that we talked about in Calc1 with regards to our usual functions, we should be able to talk about in regards to power series. And this is the start of a longer conversation, but I want to lay the groundwork here and begin looking at it in this video. Okay, so the very first thing that I want to highlight is simply that some of our favorite easy functions, polynomials, can be thought of as power series. And to sort of illustrate this, I'm going to use one example, which I think will immediately make this clear for all others, right? So let's talk about the polynomial, call it p of x. And let's just say that this polynomial is x cubed minus 3x squared plus 1. Why not, right? Again, this is just an example, but it's representative of the idea of polynomials more broadly, right? So I'm going to claim that I can think of this as a power series by rewriting it as follows, right? So I'm going to write it from smallest term going up to largest term. So we'll start with the 0th order term. So that's our 1 plus, and now the x term, well, there is no x term, right? There is no term that just has an x in it. And so I can represent that as a 0x plus, and now for the x squared term, there's a negative 3. So negative 3x squared plus, for the x cubed term, that's really just a 1x cubed plus, and because x cubed was our highest order of this polynomial, right? There's really 0 x to the fourths plus 0 x to the fifths plus 0 x to the sixths, and so on and so on. And so this really does take the form of an infinite sum, right? Sum as, let's say sum as n goes to infinity, starting at 0. So n goes from 0 to infinity of expressions of the form c sub n times x to the n, right? So this is a power series centered at 0, and we have that c sub n, right, takes on the following terms. C sub n is equal to 1 if n is equal to 0. It's equal to it's equal to 1 if n is equal to 0 or 3, right? That is the 1 here and the 1x cubed. We have that c sub n is equal to negative 3 if n is equal to 2. And we have that c sub n is equal to 0 otherwise. Right, so what we have now is I'm able to represent this polynomial in this form. And because we have this infinite trailing off of zeros for these c sub n's, it will turn out, maybe not surprisingly, that this particular power series has an infinite radius of convergence, right? So this power series truly is the polynomial in the sense that if I plug in an x value into this expression, I get exactly the x value I would expect from this expression. So polynomials can be viewed as infinite power series. At the same time, we have a non-trivial example, or at least a less intuitive example, right? Recall that we can associate this power series, we saw this at the end of the last video, we can associate this power series with this function because this was a geometric power series and we had a formula for what it converged to as long as the radius of convergence in this, or I should say the common ratio, which in this case was this x value, was less than 1. So these two expressions as functions are actually equal to each other, provided that x is less than 1. Right, so as long as we're plugging in x values, I should say absolute value of x is less than 1. So as long as we're plugging in x values that are between -1 and +1, this expression makes sense, and this power series is equivalent to this function. So we can just call them both capital F of x. Interestingly enough, we can create new power series from our old power series if we are just a little bit clever about it, right? So if I know that this expression up here is true, right? If I know that this expression is true, how can I use that information to create a new power series down here or down here? Well, what I can do, let me clear my space here a little bit. What I can do is I can think about how I go from this expression down to this expression. And all I'm really doing, notice, if I go from here to here, I'm replacing my x value with a negative x value, right? So maybe I should say I'm replacing my negative x with a positive x. So whatever I had here as a negative x, or whatever I had here as an x that I was subtracting, I think that's the better way to say it, all I need to do is replace that x with a negative x, and the result is we get a minus x, aka a plus x in the denominator. So by introducing a negative x instead of an x, I will end up with 1/1 plus x. But to do that, I need to replace my x in my series with a negative x. And so I get this new expression of negative x quantity raised to the n. And indeed, what I see is that I can write this expression as the power series sum, as n goes from 0 to infinity, of negative x raised to the nth power. Now, interestingly, we can rewrite this because that negative x to the n is the same thing as -1 to the n times x to the n. So what we really see is that what I get here is an alternating series. Let me say that I can, because I can rewrite the -1 to the n times x to the n, I can rewrite it as that. This can be thought of as 1 minus x plus x squared minus x cubed, and so on, plus x to the 4th minus x to the 5th. This is simply the alternating series version of this polynomial. Now, how do I go from there to get to here? Well, this expression is the same as this expression, except it's multiplied through by an additional x, right? So x over x plus 1 is really nothing more than x times 1 over x plus 1. And we saw before how to get 1 over x plus 1 in a power series form. So because 1 over x plus 1 is really equal to this, we can see that in this case, x times 1 over x plus 1 should be equal to x times that. And so we get this new power series. This will be x minus x squared plus x cubed minus x to the fourth, and so on, right? And so you can start to see how you can use a little bit of knowledge that we have about certain series that converge. For example, our original geometric series that was originally written up here. And we can use that to create new series of slightly different forms and be able to express, again, not a function we use every day, but this is just a nice rational function. We feel relatively comfortable with this. We can express this in a power series form. All right, great. So that's kind of a cool trick, and we can use this to develop new power series that represent interesting functions. Going forward, I want to return to our original big question about whether or not we can take the derivative of or the antiderivative of these power series, if we can treat them as functions. And the result, or I should say the conclusion that we're able to draw, is this really powerful theorem. Now, we won't actually prove this theorem in this video. I just want to introduce the theorem so that we can use it going forward. And the theorem is stated like this. I want to read along with you. If we have a power series of this form, and as I'm reading this out loud, I notice there's maybe some interesting, unfortunate confusion going from previous slides, right? So in a previous slide, we had a C sub n, and it was an x minus a. In this slide, it's an a sub n and an x minus c. That's a little sloppy, but that's okay. I should say that won't really make a difference. So this is a power series. Let's be clear, a power series that is centered at c and has these coefficients of the form a sub n, right? So this is just a regular power series, a sum as n goes from 0 to infinity. It has a certain radius of convergence, and so we are defining this power series within the radius of convergence by this function f of x. So when I talk about f of x, what I mean is the element or the number that the series converges to when I plug in that given x value and evaluate the corresponding series. So if I have this power series, and if I'm looking at an x value within the radius of convergence, and that goes from, again, it's centered at c, so from c minus r out to c plus r, then this function is in fact differentiable, and amazingly, maybe not that surprisingly, but it's very hard to show rigorously, the derivative of this, so the derivative of f prime of x, is exactly what we would get if we had wanted to take the derivative to begin with. So notice, right, and I'm going to jump up to this expression here. If I wanted to take the derivative of this, I might intuitively try to treat it like a polynomial, take this n, and sort of bring it out front, right? So multiply out front by an additional n value, and then replace the n in the exponent with an n minus 1. I might have tried to use the power rule here. And I might have tried to do that for every single term in this infinitely long series. That's the intuitive answer. It's not immediately clear that this should work, right? I mean, power series are weird objects, and we're dealing with infinity. So it's lucky, indeed, it's really amazing that this rule works. And our power series, which works for a finite polynomial, will actually work in this infinite series case as well. So we see then that f prime of x, the derivative of f, can be calculated by applying this power rule, bringing the n out front, converting the exponent to an n minus 1. We can do this for every term in this infinite series. Furthermore, the same thing holds true for antiderivatives, right? So if we think about how we might have calculated an antiderivative, again, I'll go back up to the top. How might I have calculated an antiderivative of this? Well, I probably would have tried to replace this n with an n plus 1 and then divided the whole thing by n plus 1. And I probably would have tried to do this for every single term individually, right? Just as like I would with a polynomial. So, and then at the very end, right, at the very end, I would have had to tack on a plus c for this arbitrary constant. It turns out that that rule absolutely will work when trying to find an antiderivative of our power series. So we see that not only can we calculate derivatives using the power rule, but we can calculate antiderivatives, just as we normally would, by taking our exponent raised to the n plus 1, dividing by n plus 1, we get a new power series, and then we add on this plus c to introduce a new constant term. So the short version of this powerful theorem are this. If our power series is giving us a well-defined function, then derivatives and antiderivatives work as we might hope that they would work, by treating the individual terms of our infinite summation as individual elements and taking the derivative or antiderivative of each of those separately. Furthermore, the radius of convergence for both of these new expressions, the derivative and the antiderivative, also happen to be capital R. So the radius of convergence does not change. Very cool, very powerful, and not at all clear at the outset that this is what would happen. So let's end this video by deriving a power series representation of this function right here. And this function is the -1/1 plus x squared, right? So we want to figure out what that is. So we can actually do this in a very clever way. We can make the observation, and we would have to make this observation, that if I had the function 1/1 plus x, right? If that was my starting function, and I took a derivative, I would actually get our capital F of x that's given here, right? We could do the bottom times the derivative of the top, that's 0, minus the top times the derivative of the bottom, that's just a -1, all divided by the bottom expression squared. So what we actually see is that the expression we're interested in, this expression, is the derivative of an expression we already know, right? This expression right here is, or I should say has, a power series representation. And so put that off to the side here. We can make the observation that 1/1 plus x has the power series representation of 1 plus x squared plus x cubed, right? This is just our geometric power series. And so that's equal to the sum, as n goes from 0 to infinity, of x to the n. What that means then is that I can make a, or rather I can take the derivative of this left-hand side, get the expression that I want, simply by taking the derivative of this entire right-hand side as well. And so what we'll end up seeing is that -1/1 plus x quantity squared has a power series representation that looks like this. As I go to take the derivative of this first number will just disappear. The derivative of x is 1, all right? So we start there. We've got 0 plus 1 plus x squared becomes a 2x, x cubed becomes a 3x squared. We would end up with a 4x cubed plus ... So we end up with this as our power series. And let me see here. So this can be rewritten as the sum, as n goes from 0 to infinity, of n times x to the n minus 1. And what we see now is that we are actually able to represent this function having taken the derivative of a power series that we knew to give us a brand new power series that works in this case. Hey everybody, I am back here really quickly. As soon as I finished up that last video, I noticed something a little odd and I was trying to put my finger on it. I felt like there was a mistake in this example. And it turns out there is a mistake in this example. I'm off by a negative sign. So I wanted to highlight that really quickly. I think I made a mistake. Let's see. Yeah. So I made a mistake in here. I'm actually off by infinitely many negative signs, right? Because in the end of the day, I don't actually have that 1 over 1 plus x is equal to this expression. That was 1 over 1 minus x, right? The 1 over 1 plus x was actually the alternating series. Ooh, so how does that change things? Well, the alternating series, as a reminder, it started with 1 and then it became a minus x. Let me actually make sure that I've got that right. Yeah, that's right. So it was 1 and then it was minus x plus x squared minus x cubed plus x to the fourth and so on and so on. Right, so that wasn't just an x to the n, but it was an x to the n times a negative 1 to the n as well. And so when we go to take that term by term differentiation, right, those negatives will also stay in there so that instead of having it as a 0 plus 1, it would become a 0 minus 1 plus 2x minus 3x squared plus 4x cubed minus 4x to the third. And so what we will need in here at the end is something that makes our terms negative for the odd values of n, right? So n equals 1, n equals 3. We'll need those to be odd. So we need a negative 1 to the n in here as well. So small quick fix there. Hopefully I didn't break your flow or your concentration on this problem too much. Thank you all for your hard work and your effort, and I will see you all next time.